So, good noon to everybody. And okay, some of you know that unfortunately yesterday somebody stole me my luggage with computer and everything, and USB with my presentation and so on. So that's really something which should be somehow taken into account. And so, but fortunately, my PhD student found some presentation I gave in Gaeta last year on the same theme, but it's a little bit just old-fashioned. But we could somehow a little bit modify it to get some new results there. So for those who actually had this this lecture in Gaeta, so I asked for some patience and for some tolerance, you know. So now this is outline of my talk. So that's some introduction. Then I will speak briefly of some models of growth mechanism, and then I show you some experimental results concerning the shear mode cracks and the effective threshold shear mode cracks, and then some conclusion. Okay, so you know, many things were done for mode 1 cracks and fatigue cracks and so on, and for closure and things like mode 1, but just not so much was done about shear cracks. And the reasons maybe are there are some complications, just more or less stronger than in the mode 1 case. First, this is a shear friction, of course, and this is dependent on roughness and mutual displacement of cracked flanks and material and so on, many parameters. Then there is a competition between shear modes, especially both shear modes 2, 3, and mode 1. And there are more or less unclear mechanism of mode 3 crack growth, really a shear in a shear case. So actually the friction, of course, it reduces the stress intensive factors of the crack tip, and moreover, it induced a local mode 1. So this is a quite complicated case, and the quantification of these effects is difficult. Just rough assessment can be made using some analytical or numerical models. The overview was done by, for example, by Tarantino. I was in Milan at that time, and that was a good PhD thesis. And but the estimation of effective values of stress-sensitive factors due to that problem is rather difficult. Now, there is a competition with opening mode, because some shear cracks tend to branch into the mode 1 direction, of course. That's well-known phenomenon. No. But elementary quantification of this effect is possible, but you have to know effective stresses again. So actually you can get, that's just a very old books and others proposal to use a linear elastic fraction mechanic based criterion, and then you can give this simple equation. So if this left hand side of this equation is higher than this one, so you just get a mode 1 branch in a mode 2 shear case. Mode 3 is more or less complete. Okay, now there is a difference between these two modes, and in a geometrical sense. If you have just mode 2, like this, so you can see if you, this is the ideal case, of course. So the crack can deflect like this, and you get just a common line between the crack and the branch, and so this is not so difficult for the crack to deviate to mode 1. And, but in the mode 3 case, you actually have to twist the crack to get the mode 1 support. So this is more difficult because there is one point here. So actually, in mode 2, deflection of the crack zone is rather straightforward, and you can get then a rather frictionless, shear frictionless crack growth in mode 1. In mode 3, you just have to twist the crack. So in fact, it happens on a crack, on the ledges of the crack. Or asperities, you can get a twist like that. And this leads to a factory roof morphology. Mode 1 actually. And, but if you get this morphology, you have a clumping of asperities in mode 3. So it actually reduces the crack growth rate, and it was, and then it's actually nowadays are more or less a good engineering application of this case because for example, at this Gaeta conference, Tanaka was speaking about the clamping of cracks and effects of this case, because you get an inverse notch effect in fatigue. That was really a nice presentation. Now, how it looks like. So if you, this is actually 3D stereophotogrammetry made just for mode 2 crack and branch. This is a branch. This is a pre-crack here. This is a mode 1 branch of mode 2, and this is just a final fracture. And this is the profile, you know, like this. And this is the branch, and you can see that the branch is approximately 65, 60. The theoretical value of the branch is 70, and you get a really mode 1 just. So this is very close to this value of 70. This is really mode 1 branch in mode 2. This is in an austenitic steel, yeah, near threshold. And this is mode 3 case. You see the profile like this. This is a factory roof profile. And again, you get just angles like 40, 45. That's a theoretical angle for mode 1 branch in twisting. So really mode 1 crack factory roof. Okay? But this is a big difference because here you have a smooth crack. The crack can somehow propagate like this without any friction, but this case, you know, this is the, you know, like this. This is more difficult. Now, something about the models. Actually, you have two now. Just at the moment, you have two basic, just micromechanistic models of crack propagation. The one is well known. It's actually emission of shielding dislocations for a crack tip, the blunting of the crack in mode 1 case. So this works. I will mention it later on. Rather for BCC systems where you have many available slip systems with small angles in between. But just the models concern on very simple cases. This is a simplest case, well-known simplest case. You can have configuration, crack slip configuration like this for BCC metals. And so in mode 1, this is a mode 1. Sorry, this is mode 1. Yeah. So this is blunting by emission of edge dislocations, shielding dislocations, and then the new surfaces are created here. Mode 2, the same happens in shear, emission of in-plane edge dislocations, and again creation of some new surface which is not recovered, just by the environmental effects and so on. And you can get the crack propagation. But in this case, in mode 3, in this simple model, you actually emit screw dislocations, and they are not able to create any new surfaces ahead of the crack. They create, this is a macroscopic model, they create at edges just, not ahead of the crack. So this simple model doesn't explain a mode 3 crack propagation at all. But this is really a simplest model. You can have, of course, many other cases of slip plane configuration in polycrystalline material especially. And so we analyzed this more difficult case, crack like this. And if you have a crack plane minus 1, 1. Or for example, so you have two possibilities for shear cracks. This is mode 2. You have two slip systems inclined like this, and so in this case, mode 2, so you apply the shear like this. In this case, you can get blunting, as in the mode 1. But this is not possible in mode 3, because the shear is applied like this, and the Schmidt factor is 0. So this is not possible in mode 3. But if you have a slip system like this, that are actually they have not deflected, but inclined, oblique slip systems, like this for example. So you can get some dislocations on those oblique systems, interaction of dislocation, and you get some steps at the crack from made by this, but you can get, and in a process zone here, you can get it by interaction of dislocation and creation of vacancies and twins, and other cases because we modeled it in a just a molecular dynamic model. So you can create a small cracking inside it, and then the crack propagate with the coalescence of the main crack and the small cracks. So in this case, both mode 2 and mode 3 can propagate with a similar mechanism. Anyway, so this was say emission model, or we say also deformation model. But there is another model that works if you do not have too much available slip system around the plane of the maximum shear. And this is FCC systems. So the slip system have just available slip system have a 90 degrees, so that's too much. And so Needleman and others proposed a model which is based on anti-shearly dislocation. It means an absorption of anti-shearly dislocation. And it was in mode 1, they actually proposed it for mode 1. So this is actually something. You have external sources of dislocations. And in that case, if you would like to open the crack, you have to just absorb the anti-shearly dislocations. And so what can happen? If some anti-shearly dislocations like this come from the external flexors to the crack tip, they apply an internal tensile stress field on the crack, which can be superimposed with the axial stress, and the crack can propagate by decohesion. Say a nano cleavage, like this. But what happens in mode 2 and mode 3 case? In mode 2, approach it like this. You can have just the anti-shear dislocation like this. But the problem is that if you would like to superimpose the external and internal crack field, so you just don't have any superposition of normal stresses. But if the crack would propagate like this, so that's a branching, mode 1 branching. So in that case, it immediately becomes a support of external mode 1, and you can have a superposition of the. So this model predicts a branching of the crack in mode 2. In mode 3, it's again more difficult because you have just applied stress like this. So you create a discrete steps at the crack front and so on. You can get some propagation or some branching, but it's more difficult to show because it's sterile. Okay, but anyway, this is maybe most important thing. So this model predicts actually is a branching. So in summary, we can say that maybe a mode 2 should be faster than mode 3 for many reasons I showed you. So many years ago, we actually tried to somehow to explain how the crack in mode 3 can propagate just by a mode 2 steps. Then you need a rough crack front like this. but this is always the case. The crack front in real matter is always microscopically rough. So you always have some contribution of mode 2. It's just like you have mode 3, so if you just add some resolved shear stress on these corners, so this propagation is just pure mode 2. So actually you can see that if you just consider this mode 2 propagation, so the crack can propagate like this, and you get a mode 3 propagation from bucket spiral by mode 2. So this was proposed many years ago, mode 2 control mechanical mode 3 crack growth for microfracture cracks. And now you can see here that really in a case, for example, in iron, near threshold propagation, you can see this is the pre-crack front, like this. And you can see the propagation of the cracks like this. So this is actually not pure mode 2, but significant mode 2 contribution from the crack front in mode 3 case. This is a shear direction of external mode. This is mode 3. The leg propagates like this. And this is the same case in the titanium. This is a new picture. So that was not shown in the guide. This is the titanium, and you see a pre-crack front like this, microscopically rough, and you see the various kind of crack propagation directions. There is another model by McLean and other Ritchie, that shows that if you have really a straight crack front, no need for some roughness, so you can propagate the mode 3 also by mode 2 if you have particles and the cohesion of particles, and the mode 2 cracks can propagate like this. Okay, this is experimental evidence of the fact that really if you have some particles, inclusions like that, this is a shear direction like this, it's mode 3, but you see you have always some mode 1, so you can get the striations. It's austenitic steel near fracture region, so that's high applied stress, so that you can see the striations. And you can see that the crack propagates like this. So this is mode 2 propagation, not mode, along the crack front. And this is also interesting because you have here, actually inclusion here, and you can see the propagation in mode 2, this way, and mode 3, this way. And you can see that the mode 2 propagation is faster than mode 3. Even if in this case, the K2 factor was a little bit less than the K3 of that. Okay, so summary about the models. Mode 1 branch can propagate easier under mode 2 loading than under mode 3.1. Models rather indicate faster crack growth and lower thresholds for mode 2 cracks when compared to mode 3 ones. And there is still a lack of reliable experimental comparison of mode 2 and mode 3 crack growth in the near threshold region. And so we actually focused on this, and the other problem is that to find the effective values without, this closure, shear closure. But it's not so easy. There were many things in the past made with application of tensile stress and to open the crack and so on. But this is always a mixed mode, and it's not just to correct maybe. But anyway, so the main and also measurement of near threshold mode 3 and mode 2 propagation and determination of effective thresholds for these cases. And so we did a very careful experiments for each mode, for two different geometry of a specimen and cracks, so that we were sure that everything is okay, it's transferable. For mode 2, for mode 3. I will not go into the detail for these cases, but 3 materials: arco iron, austenite, titanium, BCC, FCC, and HCP structure. And so we try to do something to separate or to delete the closure problem. So we have had a sharp notch introduced by Bell mechanism, and then we applied a cyclic compression, complete cyclic compression. And the crack can still propagate, this is well known, but you applied a small residual tensile stresses, and these small residuals open the crack. So that actually crack flange cannot somehow interact. And then you enable the stresses ahead of the crack cracks to reduce the, to remove the residual stresses, and you get an open crack, you can get the intervals. Okay. These are the results. So you have here two different specimens, CTS specimens and so-called just shear specimens, and these are the results. So this is a mode 2 for alkyl iron. Just this is the more or less the value, the threshold value, like this. This is mode 3. You see the threshold value is higher. This is mode 2 in austenite. Again, mode 2 threshold value. This is mode 3, threshold value again higher. This is a new result. This is titanium. Sorry to a few points, but you can see the threshold more or less, like this in mode 2, and this is mode 3, high. Okay, so this is the table. You can have a ferrite or iron, say, mode 2, 1.5, effective. We believe that this is effective, yeah? Or less. K3, 2.6, austenite, 2.5, 4.2, titanium, 1.8, 3.7. Well, I'm just, maybe we made an extended stereophotogrammetry to indicate how the crack propagates actually. In austenite, this was the case, you know, mode 2, mode 3, deflection, twisting, very theoretical value, 70%, very close to that. Mode 1 branching in austenite. And ferrite, very flat surface. Practically, the crack goes in shear mode along the shear mode, maximum shear plane, shear stress plane. And in titanium, there was something in between the ferrite and austenite. You know, if you see the, yeah, something in between. So in ferrite, the micromechanism of the crack growth corresponding to the emission mode of shear dislocation, because that was actually a shear mode, right? And the branching condition, I showed that similar, the simple branching by far not fulfilled, so the crack could not branch, according to this simple criteria. So that's okay. Many easy slip systems in this case. In titanium, the micromechanism corresponding to the mixture of emission absorption models. The branching condition was still not fulfilled. That it was on the boundary. Less numbers of resistors, we say. You have a basal plane in HCP metals and two other planes, pyramidal and the other slip systems. That actually these two are not easy, and the basal is easy. So something in between. In the austenite, the micromechanism corresponding to the absorption model, the branching condition was safely fulfilled. So branching occurred in this case. And this is just the last point I would like to mention. Actually, we don't know if we have really reached the effective values, but if you have an atomistic model for geometrically ideal, straightforward crack, you know, flat, crystallographically flat crack, atomically sharp crack, in a perfect iron crystal. So according to the rise, if you apply the monotonic loading, so you get this A1C value for the iron, 0.7. If you would think about a fatigue threshold, so you need that some dislocation emitted turn back to the crack tip. So this actually demands a little bit higher applied delta K effective when R ratio is 0. So this was calculated about 1 megapascal. So this is really a perfect, effective mode 2 value for iron from atomistic calculations. And our result for polycrystalline iron, as you could see, is 1.5 megapascal. So this is, the difference is not so far away from that. And it is understandable because you do not have ideal conditions. Some planting of the cracks, it's not ideally sharp, and other factors. So could be expected some higher values. So we believe that we really reach the effective values of the thresholds. Okay? So let me conclude. In alco iron and titanium, mode 3 crack predominantly propagated along the shear plane in local mode 2, but in the titanium the deflections were higher, and mode 2 cracks grew in a local mode 1, a slight 1, 2 plus 3 actually. In austenite, mode 2 and 3 cracks immediately formed mode 1 branches, deflected planes and factory roofs, as you could see before. And for mode 2 cracks, the branching condition I was showing was clearly fulfilled here. So it seems to work. And effective thresholds for mode 2 were lower than those for mode 1. So this is some acknowledgement. Thank you very much.